All right, can you guys hear me?
Yes.
All right, good. So today we're going to continue with Chapter 8, finishing it up, and we're going to begin going over some implementation of paired sample t-tests and independent samples t-tests with software. And I will announce what the structure of the next exam is going to be in just a moment. It will be on chapters 7 and 8, and we'll cover everything since the last exam. Oh, I'm sharing the wrong screen with you guys. All right, so let's continue with discussing the theory and then the practice of the independent samples t-test. So when last we left off, we were talking about how the most difficult step of doing the independent samples t-test kind of problem was figuring out the characteristics of our comparison distribution. So our comparison distribution is the same concept that we've discussed in all previous hypothesis tests, where we have a comparison distribution and we locate our sample on that comparison distribution, and then based on the parameters of our hypothesis test, including what kind of tail test and what alpha value you choose as your significant value, that determines whether or not you reject or fail to reject your sample. And this all has to do with step 2 of that classic 5-step hypothesis testing procedure. Oh, all right, so Andrea, I see your comment. That's fine. It's okay if he comes late, don't worry about it. All right, so step 2 involves multiple sub-steps where we construct our comparison distribution. And constructing the comparison distribution has multiple steps, but all of the steps, if you do them in the right order, you'll get all the information you need for each step from the previous step, and it all builds on each other. And this new distribution that will serve as the comparison distribution is what we called this distribution of the difference between means. It's a mouthful, and what it's referring to is the fact that it is a distribution that gets made when you sort of average out or merge together the distribution of means for each of the two population of distributions representing the two groups in the problem, such as a control group and an experimental group, or a drug group and a placebo group. And because you have two groups that represent two different populations, you need to create two distribution of means, sampling distributions of each of those population distributions, and then you have to combine them for the sake of actually calculating whether or not the two groups are significantly different according to the hypothesis testing steps. So if you recall last time, there was a pretty straightforward way of going about solving this problem, and I encouraged you to rely on this sheet that I made, where it has all of the distributions that you'll need, as well as all of the equations that you would use to do each of the calculations. And in all of these problems, you'll always be given enough information, usually about the two samples, that you can calculate all of the characteristics of the other distributions until finally you compute the t-score of the problem. The t-score is going to be just like the t-score for the single sample and dependent samples t-test. It'll be a fact about our two groups and the difference between them. And we'll find that t-score of our sample on our comparison distribution. And then from that point, the hypothesis testing procedure is identical to what we've always done, where we simply say, is it in the critical region, yes or no? If yes, reject the null hypothesis. If no, fail to reject the null hypothesis. So the first step of figuring out the comparison distribution is just recognizing that, just like for the depend samples t-test, we are making the assumption that if the null hypothesis is true, the mean of our distribution of the difference between means will be 0. And this reflects the fact that if there is no difference between the two groups under comparison, if you take the difference of two groups that have the same group means, you'll end up with 0 as the difference between them. So we know before the problem even begins what the mean of our distribution of differences between means will be. But what we don't know is what its standard deviation is. And all the rest of the steps are a long, convoluted way of getting that little piece of information that you need in order to calculate your sample statistic. So the first thing we have to do is we have to look to our two samples and calculate the estimate of the population variance based on the sample variance that we have. So in these problems, you have all of the data for each of your two samples, and you can calculate the variance of that, and to calculate and to estimate the variance of the population those samples come from, you use that formula where you divide by the degrees of freedom, sum of squares divided by degrees of freedom, rather than divided by n, and that gives you this calculation from figure 2a, which is the estimated population variance based on each sample. And the next step was to figure out this thing called the pooled estimate of the population variance. So two things to notice. This term, pooled estimate of the population variance, is not something we've ever had to deal with before. Previously, we've only been dealing with one sampling distribution in any given hypothesis testing problem. There was one population, sort of that was represented as a population where our scores are being taken from, and that population only ever had one variance. But here, we're actually having to have two different populations. And one thing we found last time, I think I got a little bit, let me just go back a little bit to highlight an assumption behind the independent samples t-test, where we have to assume for the problem to sort of make sense mathematically that our two populations representing the two groups in the problem have the same variance. So these two populations, which could be a drug group and experimental group, a group of rats fed a normal laboratory chow versus a group of rats fed a high-fat diet laboratory chow, we're assuming that both of these populations, even if they have different group means, we're assuming that they have the same variance. We talked last time about how this is often a mistaken assumption, or an assumption you are pretty sure is going to get violated. And there are ways to correct for it, but for the sake of this problem, we're going to assume that they are equal. And because we're assuming that our two populations have equal variance, all we need to compute is one variance term and simply say that it is the variance that is true of both of our populations. And that variance that is common across both populations is what we are calling the pooled variance estimate. And that's what we're calculating in 2b. So just to be clear, the population, the pooled estimate of the population variance is a fact about these two populations up here, the populations of scores, not the sampling distributions, which will have their own variance terms. And to calculate the pooled estimate of the population variance, there is this equation up here. It might look like there's a lot of terms to deal with, but there are only really 4 terms that you have to know. Degrees of freedom for population 1, df subscript 1, df subscript 2, which is the degrees of freedom for population 2. You need to know this term, which is the estimated population variance for population 1. Remember, S squared is the estimated population variance, and S squared with a subscript 1 means that it is for population 1 specifically, and ditto for the estimated population variance of population 2. And this other term that you need to know to plug this all in is degrees of freedom total. And degrees of freedom total is very simple. All you need to do is add the degrees of freedom from your first sample and your second sample, and you've got your total degrees of freedom. Notice that the total degrees of freedom is not the sum, it's not n1 plus n2 minus 1. It's the degrees of freedom for the first sample and the degrees of freedom for the second sample. If you were to sort of take the degrees of freedom for 2 samples that each had a sample size of 10 and calculate the total degrees of freedom, so sample 1, if it had an n of 10, it would have 9 degrees of freedom. For sample 2, if it had an n of 10, it would also have 9 degrees of freedom. So our DF total would be 9 plus 9, or 18. Do not make the mistake of assuming that the degrees of freedom total is like n1 plus n2 minus 1. So this pooled estimate of the population variance accounts for the fact that our 2 populations, we need to know their variance, or we need to sort of estimate it and know it for the sake of future calculations. And we also need to make the assumption that both populations have the same variance. And we'll see in a moment that the reason why the degrees of freedom are set up as these 2 fractions, where the first sample's degrees of freedom divided by the total is kind of like a modifier for that you multiply its estimated population variance against, and the same for the other. And the reason you do this is to account for the fact that both of the samples might have very different sample sizes. And in terms of estimating what the population variance is, you would ideally want to sort of weight higher the sample that has a larger population, because the idea is that the sample that has the higher sample size is more likely to be representative of the true population variance than the sample with the small sample size, since whenever you have a small sample size, you are more likely to get extreme and unrepresentative results. So here's an example of the calculation of the pooled variance, where if you imagine you have 2 groups with the same sample size, you have a total of 18 degrees of freedom. And if you were to plug in all the information for the pooled estimate of the pooled population variance, you would get 126.9. And I highlight this in green because I want you to pay attention to how it's pretty much exactly halfway between our estimate of the variance of population 1 and our estimate of the variance of population 2. And it's almost like you're averaging together the 2 estimates of the population variance into a single measure. And that's exactly what we need to do for the sake of that assumption that both the populations have to have the same variance for the rest of the problem. So to go back to the problem that was the bit that we were discussing here, this is the second Excel spreadsheet that we were looking at. This is the rat example where we're looking at high-fat fed diets, high-fat chow-fed rats versus normal chow-fed rats in a kind of rat diet study. So the next thing we're going to do, having figured out the estimate of the pooled population variance, is we are going to figure out the variance of each of the distribution of means. To go back to our independent samples t-test image, what we're finding out are these two facts. See, S little m, S little m. Ideally, what I should have done here, and you may want to do it if it helps, you can write SM1 to represent the fact that it's from population 1 and population 2. But what we're going to find is that it's not really going to matter so much. As long as you keep everything in a nice little column, it's not going to really interfere with your ability to calculate stuff later. But just notice that this is the next thing we're trying to calculate. So here, I actually did refer to group 1 as SM1. This is the variance, S squared. I know it's hard to see because S squared and M1 are sort of far apart, but this is an S squared term, and it has a subscript of M1 because it is the big M, meaning it's for a sampling distribution, and 1 meaning it's referring to population 1. So it is the variance of the sampling distribution for population 1. And here's the equations for how to calculate that. It's that pooled estimate of the population variance divided by the sample size of group 1 and group 2. And in this example, they both had the same sample size. So N1 and N2 were both 10. And because the pooled estimate of the population variance, S squared pooled, was also the same for both, in this example of equal sample sizes, you will have the same estimate for each of the two groups. But you can imagine that if the groups have different sample sizes, like let's say one was 9 and the other was 11, you would have slightly different estimates of the sampling distribution's variance. So now I've just plugged everything into the problem. So we've learned the total degrees of freedom for the problem. We calculated the pooled estimate of the population variance, which is to say our assumption about what the variance of both of the distributions is. Each of them is expected to have 126.9 as the variance. And we use those two bits of information to calculate these values for our distributions of means, which are sampling distributions of these populations. We calculated this one in the previous part of the problem, the variance of this distribution, which was 12.7 for both. But remember, when you calculate the variance, it's very, very easy to simply convert that to a standard deviation just by taking the square root of it. So to get this value here, SM, which we called previously the standard error of the mean, because it is the standard deviation of a sampling distribution, just the square root of 12.7 is 3.6, and because the variance is the same for both of these sampling distributions, that's how we have these values here. So we got to 3.6 by taking the square root of 12.7, because for a given distribution, the square root of its variance is its standard deviation. So the next thing we're going to have to do is we're going to have to figure out first the variance and then the standard error of our comparison distribution, the distribution of differences between means. As you can see, we don't have very much work left to do in the problem. So first, we're going to use the information we've just calculated to figure out the variance of the distribution of the difference between means. And what I've drawn in this little insert on the top right are these two arrows that kind of highlight the fact that the two distributions whose variance and standard error we just calculated, we're kind of going to fuse them together or use information from both of them in order to identify the properties of our distribution of the differences between means, which will be our comparison distribution for the last parts of the problem. So to figure out the variance of our comparison distribution, we're going to use this formula down here. And we're going to be calling this specific variance, which is the variance of our distribution of the difference between means, a sort of with a new subscript, we're going to call it S-squared difference. So we're using the word difference as the subscript, but technically speaking, the distribution of the difference between means is also a sampling distribution because it's also made of means. It's kind of like a fusion of two sampling distributions based on actual populations. For some reason, I'm reaching in my head for a reference to the anime series Dragon Ball Z, where characters sort of did a dance and they fused together. And that is kind of like what S-squared difference is. That's what the distribution of difference between means is. It is a fusion of our two sampling distributions. But anyway, to calculate the variance of the distribution of the difference between means, called a squared difference, it's simply the variance of the distribution, the sampling distribution of our first sample, our first population, and the second. So we just calculated these two values, 12.7, 12.7. And the variance of our distribution of difference between means is quite simply the sum of those two things. So 12.7 plus 12.7 is about 25.4, or rather it's exactly 25.4. And one of the things that allows us to sort of add two variances together, this might look strange, but because in the past we have always had to like calculate a variance with a kind of a formula that involved at least some division. But here, there's something interesting going on, because when we are combining two distributions of means that each have their own variance, this is something that is like mathematically possible. But whenever you combine two distributions together, you might think that you're like getting more power, or you're sort of like pooling two things that each have like some problems individually, but sort of pulling them together might actually sort of improve or increase your understanding of what you're looking at. But you actually are adding sort of more noise and more complexity. And if the general principle that we talked about way back in the class, that a distribution that has a lot of variance doesn't tell you as much about sort of what the population looks like than a distribution with very little variance, because a distribution that has a lot of variance, it's not obvious whether an extreme score is interesting or surprising, because distributions that have a lot of variance are very likely to get extreme scores. So the fact that the distribution, the difference between means, has, in this case, literally double as much variance as each of the sampling distributions, tells you something about the drawbacks of an independent samples t-test. Because the act of creating this distribution of difference between means gets us a comparison distribution that has way more variance than either of the two sampling distributions we've been using to construct it. In this case, it has literally double the amount of variance. Doubling the amount of variance is usually a terrible thing, but here it's a necessary thing. There's no way to get around it. And this is a fundamental limitation of the independent samples t-test, which compared to other hypothesis tests we've talked about is kind of a disaster in terms of like maintaining statistical power. But anyway, the very last step of the sort of second sub-step of determining the characteristics of the comparison distribution is just take the variance of our distribution difference between means and take the square root of it in order to get the standard error of our comparison distribution. So the square root of 25.4 is 5.04. And with that, we have the last fact we need to know about the comparison distribution. Because remember, its mean was already known to us. Its mean is known to be 0 because that is the mean you would expect if our null hypothesis that population 1 and population 2 have equal means is the case. So we now have those two facts about the population, about our comparison distribution, its mean, which is 0, and its standard error, which is 5.04. So in teal, I've put our 2 bits of information. And I want to just highlight the fact that if we look at our different distributions, we can actually compare all of their variances. We have 4 different types of distribution in this problem. We've got our sample distribution at the bottom. We've got our distribution of scores at the top. And then in the middle, we have the sampling distribution of each of the populations. And in the 3rd row, we have the comparison distribution that is specific for this independent sample t-test kind of problem. But let's look first at the comparisons that we should look at are the sample distribution versus the distribution of scores, and then the distribution of means versus the distribution of the difference between means. It's not useful sort of to compare the sample distribution to the distribution of difference between means because one is a distribution of scores and the other is a distribution of means, and they're like in parallel universes in terms of, it's like comparing apples and oranges. So the first thing I want you to notice is that the samples have about 120 and 130 as their variance, and the pooled estimate of the population variance is simply the midpoint, in this case, between sample 1 and sample 2. And this makes sense because we are using the variance of sample 1 and sample 2 to estimate the variance of the populations they came from. Because our best guess about the variance of the distribution of scores for population for the 2 different groups is going to be what we do know, which is facts about the sample. And because we need to come up with a single estimate of the variance for both populations, it's going to be somewhere between whatever the lower sample variance is, whether that's for population 1 or population 2, and whatever the higher one is. The pooled estimate is never going to be lower than the smaller variance population, or sample in this case, and it's never going to be higher than the sample that has the higher variance. So in our case, if you had calculated the pooled variance and got a score of 150 as the variance, you know that's going to be impossible because the pooled estimate of the population variance has to be between the 2 samples. So next, look what happens when we go into the realm of distributions of means rather than distributions of scores. Just like we've seen many times in the past, when you go from the distribution of scores to distribution of means, variance decreases. So whereas the variance of the distribution of scores pooled was 126.9, here it's 12.7. And that's simply a consequence of the fact that when you compute the variance of a distribution of means, you divide by n and then take the square root of that, which definitely gets you a smaller number. So in this case, it's about 126.7 divided by sample size of 10, and that's why you get that. But then when you combine the 2 distribution of means to create the distribution of the difference between means, you end up with approximately twice as much variance as each of those 2 individual differences, distributions of means. So 12.7 and 12.7 for each of the individual ones, but when you combine them, they have twice as much variance. So finally, we can proceed to step 3. And everything here is a walk in the park compared to finding this weird comparison distribution we call the distribution of difference between means. For this part, we can use exactly the same tools and logic as for both of the 2 types of t-tests we've learned, the single sample and the dependent samples. And we're going to use the same formula for calculating the t-score of our sample. And let's first just go over the things that we need to know in order to figure out whether to reject or fail to reject our sample score. And let's just look at, based on what kind of t-distribution we'll be using, what is the cutoff t? So I'll show you two ways of doing this. I'll show you how to do it with the Shiny app, preferred, as well as the t-table, which is linked with the other lecture materials for today, as well as in the textbook. So just like before, we need to know 3 facts about the t-distribution, because our comparison distribution is a t-test. It is a t-distribution, because this is a t-test. So we need to know the degrees of freedom, the significance level or alpha value, and what kind of tail test we're doing. So far, so good. The one thing that is different about this kind of problem compared to the other kinds of t-test problems is that the degrees of freedom we're using is not the degrees of freedom of one sample or the other sample. It is in fact this thing, the DF total, which we actually used earlier in the problem when computing the pooled estimate of the population variance. But this is easy enough to calculate because you know how to calculate degrees of freedom for each of the individual samples. It's just n-1. So in our case, we have 18 degrees of freedom. And if you recall back to the way that we set up the null hypothesis and research hypothesis, it was a directional hypothesis where we were predicting that population 1 is going to have lower scores than population 2. So just to refresh your memory about the nature of the problem, we had 2 groups. Population 1 and population 2 were groups of rats who were fed one of 2 different kinds of diet, chow. One of it was like a nutritionally balanced diet chow that typically keeps rats nice and lean, and then a high-fat, high-sugar chow that reliably makes them obese and fat. We called population 1 the rats who were fed the normal chow, and population 2 the rats who were fed the high-fat, high-sugar chow. So if population 1 is the rats who are fed the chow that's going to keep them lean, and the variable we're measuring is their body weight, we will say that population 1 is going to have lower scores than population 2. And that means, for the sake of our hypothesis testing, we're going to be using a one-tailed lower test. And we'll return to this in just a second. I'll spell it out more clearly. But that's why we're doing a one-tailed lower test instead of a one-tailed upper test, because of how we specified which population is population 1 versus population 2. And then in the problem, we stipulated that the alpha level is going to be 0.05. And those are the 3 bits of information you need for the Shiny app, or the t-table. So for a t-distribution with 18 degrees of freedom, at a 0.05 significance level, and a one-tailed lower test, there's 1 critical t-score, or cutoff t-score, and that's at minus 1.73. So this is the relevant information. But the one sort of bit of information I didn't include here, but was included in the problem, was the alpha value, which was 0.05. But everything here tells you all you would need to know. So what we're going to do at a later step is compare our sample t-score to this cutoff t-score to see whether or not it's in that critical region that's shaded over here. So finally, we can include some further information in our big table, which is the alpha value, the type of tail test, and that cutoff t-score, which we learn either from the Shiny app or from a physical t-table. And then you can see the last thing that hasn't been filled in yet is the t-score. So calculating the t-score is fairly straightforward. It is simply going to be our difference between the 2 groups, where the mean of group 1 and the mean of group 2, or which is to say sample 1 and sample 2's means, we are going to simply calculate them like that and make sure that you are subtracting M1 minus M2, not the other way around. It's very important that they be in this order. and then we divide it by this S difference. If you recall, this was what we worked so hard to find through all of those intermediate calculations. That was this value down here. S difference of 5.04. All that work we did was just to get that value so we can find the right t-score for our sample. But once we have it, it's a simple matter to calculate the difference between sample 1 and sample 2's means, divide it by 5.04, and that gets us a t-score of minus 1.87. So now the last step is to figure out whether our sample t-score of minus 1.87 is more extreme or not extreme enough to reject the null hypothesis. First, I've included our t-score here. This little diagram here doesn't have the one-tailed or two-tailed or directionality, just because for different problems it might be different. But if you know about the one-tailed, oh, sorry, this actually is a, hold on, just a second. This is actually a mistake. I wrote one-tailed upper here. That is not correct. This should be a one-tailed lower test. That is an error on my part. I'm going to change that. Can't believe I did that. This is a one-tailed lower test. Do not believe what you see right there. This is what your distribution will look like. This is a representation of your comparison distribution, the distribution of difference between means. It is a t-distribution with these characteristics. And for a t-score of minus 1.87, we compare it to the cutoff t of minus 1.73. And lo and behold, we find that this sample t-score is in this region of rejection. It is more extreme than the cutoff value, and we can conclude that the null hypothesis should be rejected. And because the nature of the problem was comparing two different groups of rats fed two different kinds of diet, we would conclude that there is sufficient evidence to justify the claim that the high-fat diet-fed rats weighed more than the normal chow-fed rats. Not too surprising, but in this hypothetical example here, that's what we found. Now, reporting results. Reporting results is important both because it is a succinct way of telling other people what you found, and it's also good for your ability to interpret other people's research because they are going to be presenting their t-test results using this format, if they are psychologists or most other kinds of social scientists. Though, because this is a kind of t-test where there were some differences to the other ones, there are some things to sort of think about when reporting the results here. So here, you write t, and you don't write the degrees of freedom for one group in particular. You actually write df total, which was, in our case, 18. And then you write the t-score. You write the p-value. If it was less than your critical value, just write less than whatever your alpha value was. If it was greater than your alpha value, you tend to report the actual value of the p statistic. And then you report what kind of tail test you did. And if you did a two-tailed test, you generally just don't report anything, and people will just assume you did a two-tailed test. If you want to find the p-value of your t-score, if you just want to know it, or you want to be able to report it if you got a finding that wasn't statistically significant, you would go to the Shiny app, and instead of doing the adjust probability option in this first box on this drop-down menu, you would choose the adjust x-axis quantile value for the same degrees of freedom, for the same kind of tailed test, and you would put in your t-score. So for a t-score of minus 1.87, which here I think I rounded it to minus 1.88, it tells you that the p-value associated with a t-statistic of minus 1.88 for a t-distribution with 18 degrees of freedom with a one-tailed lower test is 0.038, and 0.038, that is less than the alpha value, and so that's just an alternate way of calculating whether, that's an alternate way of deciding whether to reject or fail to reject the null hypothesis. I guess even though this is like the common way of sort of presenting your results, I really like using the visual demo of it, just to see the distribution and see where your sample statistic falls in a distribution. It's just a visual way to do it instead of just looking at two numbers and deciding which is larger or smaller than the other. So in the example that we just did, both groups had 10 animals in each group, 10 subjects per group. But this is not usually going to be the case with experiments you do. Because if you can imagine, even if you had a experiment in mind where you wanted to have exactly 100 subjects in each group, it's likely that someone wouldn't show up for their experiment, or you would sort of lose some data by accident if you were careless, or your lab assistants were careless. So you might end up with unequal sample sizes, even though you intended to have equal sample sizes at first. And you obviously don't want to sort of discard perfectly good data from one group just for the sake of having an equal sample size. You would actually sort of lose power if you do that. Even though it's easier to calculate if there's equal sample size. Well, even though I say yes, it's easier to calculate, but it's only easier to calculate if you are sort of committed to doing things by hand. But as we'll see, there's no reason why you would have to or want to do this kind of labor-intensive calculation process by hand when software is available. But let me just quickly show you how things are a little bit different when there is an unequal sample size across your two groups. So in the second tab of our rat weight example, we have the unequal sample size condition. So in this condition, just like before, the normal child group has 10 rats and they have the same weight data as before, but I have just simply omitted the last data point for the high-fat, high-sugar chow-fed rats. So instead of there being 10 rats in this high-fat, high-sugar chow-fed group, there's only 9. That has some implications that are obvious, like when you're calculating the sample size, it's 9 instead of 10. The degrees of freedom, instead of being 9, they're 8, because the degrees of freedom of n minus 1 is 9 minus 1. The mean is going to also change because one of the values is now different. Its variance has increased compared to before, and its estimated variance has also increased. Typically, but not always, but when you sort of omit samples from your, when you omit subjects from your samples, you're going to increase your variance because smaller sample sizes generally have more variance. This is not always true. If you have an outlier data point, like that's very extreme in one direction, then taking that out of the calculation would, in fact, result in less variance. But as a general matter, when you are sort of lowering sample size, you are increasing variance for the sample. So that's something that you can definitely sort of do as an example, but I want to emphasize to you that there really is no reason to go through all of the trouble of calculating the independent samples t-test stuff by hand when software exists. Let's actually go to JASP for a second. If you remember all the way back, JASP was a software tools that we use to calculate various things of interest. And one of the things that JASP is able to do is it's able to do a independent samples t-test. So let's take our Excel file And we're going to do a little bit of a refresher on not just how to conduct this analysis in Excel, but also how to take data that is sort of written out in Excel in the Excel spreadsheet and put it into a format that's suitable for JASP and SPSS and other kinds of statistics packages. And the very last thing we'll do today before I explain what the next quiz is going to be about is just go over how to calculate effect size and power for the independent samples t-test and compare it to a dependent samples t-test with similar characteristics. So here's our rat weight example in our Excel spreadsheet. Let me just zoom in a little bit. So in this spreadsheet, I have sort of done all of the work that we did by hand, or by hand in quotes, in Excel, in PowerPoint. And you could do all of this, like follow along with these steps and sort of try to stay organized when doing sort of your own t-tests or answering quiz problems. But I will tell you there's no reason to do this. You see how like color coding things is really necessary because you have so many different terms, and dealing with like writing little subscripts so that you know which kind of samples you're referring to and which kind of distribution you're referring to. It's really difficult in Excel because Excel doesn't, like, it's not very good at it. This is not what Excel is meant for. Excel is meant for being like a calculator and a way of like organizing data. So you have to like annotate your work in a way that is really complicated. Like it takes a while, like for me to do this, it's helpful to figure out a way to sort of like draw borders around things and color in cells with different colors. And this is just a lot of work, and I don't want you guys to have to do that. So down here, if you scroll down to the bottom part of our Excel spreadsheet, there's actually, here is just an overview of calculating the t-score, and then I got a screenshot of the t-distribution Shiny app to sort of, this is exactly what we saw before, there's no difference. And I also calculated the p-value, concluded it's less than 0.05, so we would reject the null hypothesis. And all this work that we did up here, where we're sort of calculating things in different columns, where on any given step you could make an error and you have to sort of do some work to annotate it, you could just see how I got this little box here, or ... and then 0.038, which should look similar to this cell with our p-value calculated of 0.039. Yeah, so this cell right here, if we were to inspect the, let me just, oops. I'm going to just increase the size so you can see the formula more easily. So all that work can simply be replaced by knowing how to do the Excel formula for a t-test. So here, the Excel formula is 4 different things you need to specify. Array 1, like if you don't know what an array is, I honestly don't know exactly what it is, but basically that means highlight all of the scores in group 1, and then array 2, which is in red, highlight all the scores in group 2. So let me actually just scroll up and see how this blue highlighted area, that's array 1, cells C7 to C16. So you're just like taking the data from sample 1, comma, take the data from sample 2, click another comma, and the next part of the Excel function for t-test, which is conveniently called t-test, is tails. Do you have a one-tailed test or a two-tailed test? And in our case, we had a one-tailed test, so that's what we wrote. This next one, type, let's actually just click that it gives you three possibilities. So it's a drop-down menu. I don't know if you guys can see this really well. Unfortunately, the cells are very, very small. So if you clicked 1, it would do this, assuming that you were doing a paired sample t-test. Remember, a paired sample t-test was that kind of classic before and after design. And that would tell Excel to kind of assume that the two groups of data you had were from the same subjects, and that one was just a before score and one was an after score. But that's not what we have here. We have two different groups. We don't have the same subject. And 2 in this type drop-down menu was 2 sample equal variance, and then in parentheses, homoscedastic, which means equal variance. And then 3 is 2 sample unequal variance. Now, if you recall all the way back to early in today's lecture, I mentioned that one of the assumptions of the kind of t-test that we're doing is that both of the samples, both of the populations, have equal variance. Remember, that was an assumption. We calculated that pooled variance. Well, now I can tell you that that is not necessarily something you have to assume for the sake of doing a t-test problem. In order to sort of make sure that I got the same p-value as we calculated by hand, I sort of did that because that was an assumption. But notice that this is not something you have to assume. And I would actually just encourage you guys to think about, do you think that you are more likely to reject the null hypothesis or less likely to reject the null hypothesis if you assume that the two populations have the same variance, or if they have different variance? So either you assume that the two populations representing population 1 and population 2 have the same variance, that same pooled estimate of the population variance, or you can assume that they don't have the same population variance. Which do you think gives you more power? So making the assumption or not making the assumption? Do you think that it's like, if you were a researcher, do you think that you would want to be able to assume that your two populations have equal sample size, or would you rather not make that assumption? Well, let's actually see what happens when we choose option 3 instead of option 2. Well, here it's actually going to be the same because they're equal sample sizes. But in general, when we're going to see this, an example of this in just a second, but in general, the assumption that the two samples have equal variance, or the two populations have equal variance, that is an assumption that usually loses you power. Because the more assumptions you make, the more kind of understanding you think you have about sort of how the problem works and what you know about the populations. So in general, when you assume that the two populations have equal variance, you get more power. But there are times, like we talked about, where you expect that a group that's getting some kind of experimental treatment, some will have like extreme positive effects, some will have extreme negative effects, but you do expect increased variance. So let's actually go about creating a CSV file from this kind of data set. So if you recall, a CSV file, the best way to create it is to make a new Excel spreadsheet and make something that's pretty simple, all things considered. Pretty bare bones. Compared to the kind of Excel spreadsheet that we were just looking at, which has different colors, borders, all that stuff, our CSV file here is going to be much, much simpler. I'm literally going to create 2 different columns here. And I want you guys to sort of pay attention to how I'm constructing this CSV file for an independent samples t-test. because it's not like totally intuitive how you would do this. So one of the things you might think that you would want to do is you might want to sort of include a column for rat1, rat2, rat3, up through, in our case, rat20. But you actually don't want to do this, or rather there's no reason to do it unless you somehow, for some reason, want to like care about identifying each animal after the fact. So we are going to create two different columns. We're going to create a diet column, and we are going to create a weight column. So what we have here is one variable, which is our dependent variable. So in this study, we had an independent variable and a dependent variable. Our independent variable was diet. We had rats, and they got either put on a high fat, high sugar diet, or they got put on a normal chow diet. So let's call NC normal chow, and we'll call the other one HFHS. I'm now just going to take this NC, and I'm going to sort of drag this down, and I can just make sure that I have the correct number of normal chow rats. So if you look down at the bottom, it just tells you the number of cells that are being highlighted, which is 10, which makes sense because we have 10 rats. And then I can just take our data, I can sort of paste it with just the values. So the reason why you see some decimals here is because this was actually from real data, and when we weigh our rats, we sort of weigh them with multiple decimal places. So that's why there's a difference. And then I'm going to do the same thing for the high fat, high sugar chow guys. But here I can just take all of their weight data, and then in the next row of our spreadsheet, paste it. And in terms of what to call this diet group, HF, HS, high fat, high sugar, and I can simply drag those down. And what we have here is what a good CSV file for an independent samples t-test would look like. You have your independent variable, diet, and you have your dependent variable, weight. First thing I'm going to do is I'm going to save as. Let's save this into data sets. I'll call this rat diet independent samples t-test. And I'm going to make sure that I save this as the CSV type of file. So CSV is down here. There's multiple different types of CSV. Like, I don't know what happens if I would try to do this in the MS-DOS or Macintosh version or the UTF-8 version, but there's just one that's like CSV basic, and just save it like that. So that's just a review of how you would go from a spreadsheet that is kind of useful for recording information in, like this spreadsheet here, how to go from that to a spreadsheet that, or a data format rather, that is compatible with software that can do actual like good data analysis. So let's go back to our friend JASP. And for now, we'll just see what JASP does. We saw that Excel can get us exactly the same value as we had for our data. So once we're in JASP, we're going to just open up our recent files. So here's our file, rat diet independent samples t-test. Because this is a CSV file, JASP is going to know what to do with it. JASP does not know how to deal with a Microsoft Word file, I don't think, and I'm pretty sure it definitely doesn't know how to deal with a Microsoft Word file that looks like the class example that we were just looking at. So when I do that, the first thing you'll notice is that JASP imports the data and presents it in this kind of format, where you have the same kind of structure. You have two columns with our two different variables. There's our diet variable, and there's our weight variable. Remember, we want to check to make sure whether JASP has correctly identified what kind of variable diet and weight is. So if we click on diet, we see that JASP has automatically classified it as a nominal type of variable. That's correct, because diet is a nominal type of variable. It's a category. It's either high-fat, high-sugar chow or normal chow. JASP has also correctly identified the weight variable as a scale type. It's not nominal, because weight can sort of be a continuous fluctuating number. And it's not ordinal, because we're not like ranking the rats in terms of third heaviest, 23rd heaviest, etc. It's a scale type variable. And this far left column, these row numbers, those represent these things that we called earlier on in the class cases. Cases are experimental units for a study, and in our case, they refer to individual rats. So each rat, all 20 rats in our study, had two different variables associated with them, or two different scores, you would say. So rat 1 has a score for its diet variable. It got the normal chow, and it has a weight of 340.21, in this case, grams. So we have 20 rats, so 20 cases, two variables. There are two scores per case for a total of 40 scores. But we actually only care about the weight scores. We can pretty clearly see that there's 10 of each of the two different kinds of diet. Anyway, so the next thing we're going to do, once we made sure that our data is formatted correctly, because if it's not, then JASP is going to be confused and give us the wrong information, we're going to go up to this handy-dandy t-tests button at the top of JASP. And there's classical and Bayesian. I'm not 100% sure what Bayesian is in terms of a t-test. Bayesian is a type of like statistics that has like a different foundation to it. So it gives you the three different kinds of t-tests: the one sample t-test, paired samples t-test, and independent samples t-test. In our case, we're using the independent samples t-test, but the paired samples and one samples are also pretty straightforward. So click independent samples t-test, and that little black square was a little weird, but it went away. So we have two different options to sort our two variables into. We have a diet variable and a weight variable. And we actually have two different options. We can sort diet into grouping variable, or this sort of thing called variable up here. The grouping variable is actually where our independent variable goes for this kind of problem. So select diet and click here. So diet has moved into this grouping variable. And if you think about what a grouping variable means, it is a variable that identifies each case, or each rat subject in this case, as being belonging of one to two different groups. In this case, two different groups that are being compared. And then we can move weight simply to the other variable slot. So what you notice here is that for an independent samples t-test, it gives us the same value of t. Remember, our value of t was, well, actually, we calculated t as minus 1.88, but here it gives us t as, hold on, I just want to make sure I'm not messing something up. All right, I'm just going to increase the size of this so you guys can see it more easily. So let's look at this little table up here, where this is the results of our independent samples t-test. And we have a t-value of 1.878, which should look fairly familiar because this was the t-statistic we computed for the problem itself. But however, when we computed it, it was actually minus 1.88. And just like before, the difference between 1.88 and minus 1.88 is actually not a big, it doesn't matter because like the distribution is symmetrical and it is, what's the right word? It's arbitrary which population or which sample you chose to be population 1 and population 2. So if you had sort of formatted the problem differently, you can always get a positive or a negative value of t. And for the sake of these problems, you will always see them presented as a positive number. And you'll notice that it recognizes that we have 18 degrees of freedom. But you'll notice that the p-value it tells us is actually different than the p-value that we got in Excel. What explains this? Well, if you recall, we were doing a student t-test. And here, this alternate hypothesis thing actually tells us what kind of basically this is what kind of tail test do we want to do. So this is stating the tail test as 3 different research hypotheses. Group 1 does not equal group 2. That sounds to me like an example of a non-directional two-tailed test. This one here, group 1 is greater than group 2. That sounds kind of like a t-test where the tail test is a one-tailed upper test. And then this one here, where group 1 is less than group 2, that's a one-tailed lower test. And if you recall from this problem that we just did, that we've been working with today, we've been assuming that we are doing a one-tailed test. And specifically, we assume that group 1 is going to be less than group 2. Oh, okay, so one thing that, see, it sort of generated something here, and it gives a p-value at 0.96, and it actually gives us a note because JASP realizes we might be confused about something. And I'll explain to you why JASP JASP didn't get confused about this, but why this happened. Because there is no way in JASP to specify which population you mean is group 1 versus group 2, I think it might default to like the first in the sort of list of subjects or alphabetical order. But basically, JASP misclassified or classified differently which sample was population 1, population 2. But if we click this, let me just, I need to double check that what I think JASP did. All right, I think what JASP did was it did not know, because I didn't give it any instructions about whether the normal child group should be group 1 or the high-fat, high-sugar diet should be group 1. And because JASP doesn't have any instruction about which group to assign group 1 versus group 2, it decided, well, I'm just going to probably do it by alphabetical order. So it assigned group 1 or population 1 to the high-fat, high-sugar chow-fed group, HFHS. Whereas in the problem that we were just solving, I just arbitrarily assigned population 1 and sample 1 to be the normal child group. So that's something to keep in mind with software. If you don't specifically tell it to do something, it will default to some rule that you didn't even think about. So here, I just decided to call population 1, sample 1, the normal child group, but because there was no way of specifying that in JASP, it defaulted to alphabetical order in terms of how the group 1 and group 2 were sorted. But anyway, that's why when I tried to just now do the group 1 is less than group 2, which would have been the correct research hypothesis, alternative hypothesis for the problem that we just worked out, here I actually have to make it so it's a one-tailed upper test, because that is how JASP had classified the data. And if you do that, and it is the correct value, you'll see that the p-value is 0.038. And the reason why it was, I think, 0.077 before was the default was for a two-tailed type of test. But for the kind of test that we actually worked out, we see that the p-value is exactly the same as the p-value we got previously. And in addition, something that's really cool about JASP is that you can calculate things like the effect size. So there are different kinds of effect size, like we've been talking exclusively about Cohen's d, but there are other ones. And we also talked about confidence intervals. So here, you can choose a 95% confidence interval, like let's say you wanted to know the confidence interval, 95%. Let me just, so what we have here are the confidence intervals. And notice that it gives us confidence intervals not in terms of the raw scores themselves, but in terms of Cohen's d. Now, when we learn about this thing called a meta-analysis and this type of plot called a forest plot, which is sort of a way to sort of look at multiple studies and their effect sizes, comparing them, it'll make sense why the default here is to compute the confidence interval around an effect size, not around like a score or the raw scores. But that's just a little bit of a preview of what we're going to look at later. We can look at the descriptive statistics for each of the two groups. And I think it's really cool that the descriptive statistics they're so easy to get. You just click a button and it tells you the two different groups, high fat, high sugar, normal chow. The fact that high fat, high sugar appears sort of first on the list, that's a clue that JASP sort of classified that as group 1, whereas that's not what I did. And it tells you the mean, standard deviation, the standard error. You can also generate plots of the descriptives. So what we have here. So here it shows us as a line, and it shows us the confidence intervals around the two group means. So you have the high fat, high sugar chow and the normal chow. Ideally, this would be presented as a histogram, but when it comes to like quickly looking at plots like this, a lot of these stats programs will just default to showing you these line things because I think they're just very generic. And it's like a very, very easy way to sort of see the difference between two groups because there's literally a diagonal line highlighting them. And down here we have an option called the assumption of normality. Well, two assumption checks. Remember, the normality was an assumption that we had for this kind of thing, the all t-tests. And we also had equality of variances. Now, equality of variances is interesting because that should remind you of something we talked about just a little while ago about our assumption that the two populations that are the population representing sample 1 and sample 2 have equal variance. And we can actually test that. There's a statistic for sort of testing whether or not that assumption is met based on the kind of sample you have. So let's click on the normality check and the equality of variances check. I won't sort of make you learn this, but I just want to see what we get. And what we have here are our assumption checks, sort of in between the result of our test, where we have like the p-value. Our assumption checks are using the Shapiro-Wilk test. And if you remember, the Shapiro-Wilk test, oh, here it helpfully tells you significant results suggest a deviation from normality. And the Shapiro-Wilk test statistic is capital W, and it is a test statistic that can be calculated or tested with a p-value. And because the p-value is 0.402 and 0.69, that is not significant. it would be significant if it was below 0.05 or 0.01, depending on how you chose to set your threshold. So we could actually say for these data that they are both normally distributed according to the Shapiro-Wilk test. And the test of the equality of variance is much the same, where a significant result means that the two groups have very, very different variances. But what we find here is that this statistic called F and this kind of test called the Levine test finds that it has a p-value of 0.55, which is also very unlikely to be significant if you use the class of the conventions of p-value as 0.05 or 0.01. So I'm going to save this and post this to the lecture materials for today, as well as this lecture itself will be posted. And the very last thing that we'll do today will just take us to the end of today's class. And I will send you guys an email about the quiz, which will not be an in-class quiz. It'll be a quiz that will be posted this Thursday, and you'll have until Tuesday at 11:59 p.m. to do it. I think you guys will find that quite fair. But the estimated effect size is what we have here. It's the difference between the two group means of our two samples divided by the pooled standard deviation of the two populations. So not the pooled variance, the pooled standard deviation. And some of you might have wondered why I did some sort of extra unnecessary calculations for calculating stuff in this problem, where like I didn't need to calculate the S pooled, which is the standard deviation of our two populations. But I did because I anticipated we would be using it for the estimated effect size. So in this example, the effect size is going to be the difference between sample 1 and sample 2's means divided by the square root of 126.9, which was the pooled variance. And to get the standard deviation, it's to get you take the variance and then just take the square root. And we find that there is a large effect size as a result of the diet intervention, the diet study variable. And this makes a lot of sense because it's very widely known and well understood that diet plays a very large role in body weight. So this is an example of the fact that just because something has a large effect size does not necessarily mean that it is like meaningful in some kind of clinical sense. And this is something we'll have to cover next time, but in terms of actually doing this sort of thing for because of the sample sizes might be different, if you actually cared about figuring out statistical power by hand for some crazy reason, you would actually have to create something called the harmonic mean of the two groups rather than just the mean of the two groups. And this is something we'll have to cover next time, in addition to the software stuff, where statistical power, essentially, you lose a ton of statistical power by doing an independent samples t-test rather than a dependent samples t-test, for example. All right, that takes us to the end of the class. I'll post this up on the YouTube channel, and I'll post the JASP output as well as the CSV file I generated, so that you guys can use that as a model for stuff we do further on, as well as the quiz. I will talk to you guys soon.
Bye.